we shall discuss some extra results about these spheres. Here we shall discuss about the angle of intersection of two non-concentric spheres. That means we shall consider two spheres whose centers are not concentric to each other. So over here we are considering two spheres. Say S1. Let us suppose that this S1 be one sphere and S2 be another sphere having this kind of equations. Over here we suppose that R1 and R2 is R1 and R2 be the radii of these two spheres, and suppose this C1 and C2 be the centers of these two spheres, as I have demonstrated over here by this picture. Over here, so this is the center C1 for the first sphere S1, and this is the center C2 for the second sphere S2 is equal to 0. And we suppose that distance between these two centers C1 and C2, this distance is equal to the distance small d. You see, we can find the coordinates of C1 and C2 from the equations of the spheres S1 is equal to 0 and S2 is equal to 0. And from these two coordinates, we can compute the distance C1 C2, that is equal to the distance d. And what is the angle between angle of intersection of these two spheres? The angle of intersection is defined as the angle made by the radius r1 and r2, these two radius, that is the radius cp1. This is the radius cp1, this much is the radius cp1, and this much is the radius cp2. So the angle between these two radius, that is the angle theta between the spheres S1 and S2. And in such case, this angle will remain fixed, because you see the angle, the whatever be the position on the intersection of these two spheres C1 and C2, the if you consider the section of these two spheres and take any point P on this section, then the angle theta would always be same. Let us try to explain this one by this kind of picture. You see, over here we consider two spheres. This is one sphere, the red sphere, and suppose this is the green sphere, and we consider their section. What is the section? You see, the section would be clear over here. This is the section. Let me suppress one such sphere. You see, then we would have this kind of section given by this blue line. Hmm. Then this kind of section would be the intersection of the spheres. One is this green sphere, another is this red sphere. Okay, so this is the intersection, the circle of intersection of these two spheres, and on this circle of intersection we consider any arbitrary point over here. This is an arbitrary point, and now if we just change the position of this arbitrary point, then you see over here you can consider this animation. You see this point C is changing, and in order to make it a little clear, let me suppress this circle and this sphere, and you see, let me suppress this second sphere as well. Then this A and B, these are the two centers of the sphere. This is one center and this is the second center, and you see this angle between these two radius vector, this angle is highlighted by this kind of green line, and over here you see this angle is always fixed whatever be the position of the point on this section. So in this way we find the angle between these two spheres. Okay, angle of intersection between these two spheres, and this angle of intersection can be formulated in this fashion that say if this angle is theta, then we observe that these 3 points C1, the first center of the first sphere, the point C2, the center of the second sphere, and any point P on the section of these two spheres, then these 3 points C1, C2, and P, they together form a triangle, and this angle theta is C1P C2. The angle is C1P C2, that is the angle theta, and from the formula of triangle we can say that cos theta can be written as r1 square plus r2 square minus d square divided by 2 r1 r2. So in this way we can find the angle between these two spheres, the angle of intersection between these two spheres. And we know that this angle of intersection will be a real angle whenever this cos theta lie in between -1 and +1. And in such cases, if we put the expression of this cos theta from this result over here in this inequality, then what we get this kind of inequality that -2 r1 r2, that would be less than or is equal to r1 square plus r2 square minus d square, and that is less than is equal to twice r1 r2. And from the this one inequality we'll find that r1, this first inequality we'll find that r1 square plus r2 square minus twice sorry plus twice r1 r2, that would be greater than is equal to 0. This is one inequality, and this implies that r1 plus r2 would be greater than, or r1 plus r2 would be greater than or is equal to d. And from the second inequality, this kind of inequality, what we observe is that r1 square plus r2 square minus twice r1 r2, that would be less than or is equal to d square, and this implies that modulus of r1 minus r2, the difference in between r1 and r2, this difference should be less than or is equal to d. So these are the two conditions imposed on r1 and r2 and the distance d, so that this angle theta would be a real angle, and cos theta would lie in between -1 and +1. Particularly when this equality occurs over here, when r1 plus r2 becomes is equal to d, when this equality occurs, then r1 and r2 becomes is equal to d. And what is the meaning? The meaning is that that the spheres are touching each other in an external fashion. One sphere is touching the second sphere externally, and if r1 minus r2 becomes is equal to d, is this modulus distance r1 minus r2 becomes is equal to d, in that case the spheres touch each other internally. Okay, the spheres with radius r1 and r2 would touch each other internally, and sometimes these two spheres touch or cut each other orthogonally. In that case, you see theta would be is equal to pi by 2. And over here in this formula, if we put theta is equal to pi by 2, then what we get? Then we get cos of theta would be is equal to 0. Okay. So if cos of theta becomes is equal to 0, then this numerator should be is equal to 0. And from this result, we can say that r1 square plus r2 square should be is equal to d square. So r1 square plus r2 square is equal to d square. This is the condition under which the given spheres s1 is equal to 0 and s2 is equal to 0 will cut each other orthogonally. Okay, they will cut each other orthogonally. And what is r1? R1 can would be computed in this fashion. That would be g1 square plus f1 square plus h1 square minus d d1. That would be the expression of R1. Similarly, we can compute the expression of R2. And as we know that C1 and C2, the coordinates of C1 and C2, so we can compute the distance in between C1 and C2. That would be is equal to D. So if we put the expressions of R1 square, R2 square, and D square in this relation, in that case, that result can be simplified, and ultimately we will get this result, that this relation, that twice G1 G2 plus twice F1 F2 plus twice H1 H2 would be is equal to D1 plus D2. So this is the condition under which the spheres S1 is equal to 0 and S2 is equal to 0 will cut each other orthogonally. Okay, so this is under this condition, these two spheres will cut each other orthogonally. Now let's discuss about the radical plane and radical line. What is a radical plane? Radical plane is actually the locus of a point P, locus of a point P such that the power of this point P with respect to the spheres S1 is equal to 0 and S2 is equal to 0. The power of these two of the point P with respect to these two spheres become equal. All right. So how do we define the power of a point P? I discussed them in the last lecture. That power of a point P is actually defined by the square root of this kind of expression, that alpha, beta, and gamma, these three coordinates, these three expressions are put in the equation in the expression of S1. Then we will get alpha square plus beta square plus gamma square plus twice G1 alpha plus twice F1 beta plus twice H1 gamma plus D1. So in this way, we would be able to find out the power of the point P with respect to the sphere S1. Similarly, we can compute the power of the same point P with respect to the second sphere as the square root of this kind of expression, like alpha square plus beta square plus gamma square plus twice G2 alpha plus twice F2 beta plus twice H2 gamma plus D1 D2. All right, so if these two expressions become same, in that case we can equate them. And what we observe that this alpha square, then beta square, and then gamma square, these three quantities will get cancelled, and ultimately the result what we get is this kind of result. Therefore, from this result we can compute the locus of the point P, and that locus is called the radical plane of these two spheres S1 and S2. So if we put x in place of alpha and y in place of beta and z in place of gamma, we will be able to compute the locus of the point P. So over here, what we observe is that this is the locus of the point P, that is actually the radical plane of the spheres of these two spheres. S1 is equal to 0 and S2 is equal to 0. And if we observe this a bit carefully, we can observe that this left hand side is nothing but is equal to the difference of S1 and S2, these expressions of S1 and x2. So S1 minus S2 gives us S1 minus S2 is equal to 0, gives us the equation of the radical plane over here. Now, suppose in place of two spheres, we consider three different spheres. We consider three different spheres. Then, from this, from three different spheres, suppose this is one sphere, this is another sphere, and say this is another second sphere, and this is suppose the third sphere. And then we can compute the radical plane of the first sphere and second sphere. We will get a radical plane. Then we can compute the radical plane of this second sphere and then third sphere. Then we will get the radical plane in between two and in the sphere number 2 and sphere number 3. And it can be shown that the radical plane of the third sphere and the first sphere, all these three radical planes are passing through a single line that is called the radical line. Okay, it can be shown that all these three radical planes are passing through through a single point, single line, that is called the radical line of these three spheres. So this is, in this way we can find out the radical line. And if the spheres are if the equations of the spheres are given in this fashion, suppose the equation of one sphere S1, in which the coefficient of x square, y square and z square is not always equal to 1. Maybe the coefficient is equal to a1, and the equation of the first sphere is written in this fashion, say given by this equation number 1. And suppose there is another sphere S2 in which the coefficient of x square, then coefficient of y square and the coefficient of z square, these three coefficients are same and equal to a2. And say this is the equation number 2 of the sphere, second sphere S2. All right. In that case, you see S1 can be written in this fashion by dividing the entire expression of S1 by the coefficient A1. We can write the equation of S1 and write them as the equation number 1A. Similarly, the equation of S2 can be written in this way, and let us denote it by equation number 2A. Then what would be the radical plane of these two equations? Say this is the sphere 1A and the sphere 2A. Then what we observe, the radical plane would be computed just by subtracting the second equation, that means equation number 2A from the equation number 1A. And in that case, you see this x square plus y square plus z square, these three terms will get cancelled. Ultimately, we will have this kind of expression: this quantity minus this quantity is equal to 0. So, so you see, we can also write it in this way. Suppose this x square plus y square plus z square, this is one expression, minus minus what? Minus this kind of expression, x square plus y square plus z square minus this kind of expression. And what is this? This expression is nothing but is equal to s1 by a1, and this second expression is nothing but is equal to s2 by a2. So this equation can be simplified, and the radical plane can be written as s1 a2 minus s2 a1 is equal to 0. So if the coefficients of x square, y square and z square, the coefficient of these three are not always equal to unity, in that case the formula for radical plane will be computed by this kind of formula. Let me show you the picture of radical plane over here. And over here, the radical plane, let me firstly make these two spheres visible. And over here, let me consider the radical plane. You will see that radical plane is nothing but the plane through this through the section of these two spheres. Okay, so this is the radical plane, and you can look at this expression over here. From this, look at this picture over here from the different directions, and this is the radical plane. Okay, so this is the radical plane from different orientations. So radical plane is actually the plane that always passes through the section of these two spheres. Okay, so this is the animation from different directions. So hopefully this is clear that the radical plane is actually a plane passing through the section of these two spheres. So that is the idea of radical plane. All right. And now let me let me discuss about the coaxial system of spheres. Now, what is coaxial system of spheres? Coaxial system of spheres. So suppose we have two different spheres. Actually, let us consider a system of sphere. Over here, you see, system of sphere means we consider more than one sphere, and that may be number of two spheres, three spheres, four spheres, maybe infinitely many spheres. So they together form system of spheres. Now, this system of spheres is said to be coaxial whenever any two of these any two of these two systems, I mean, if you consider any two spheres from this system of spheres, then the radical plane of these two spheres must be same. So on the system of spheres such that any two of them have same radical plane is called a coaxial system of spheres. So suppose we have 10 different spheres. Then if it is possible to find out the result that if you consider any two out of this collection of 10 different spheres, if you consider any two spheres, and if it is found that any two arbitrary spheres from this collection have same radical plane, all right, then only this total collection of total collection of spheres will be called coaxial system of spheres. That is the definition of coaxial system of spheres. Now, how to mathematically get an idea about the coaxial system of spheres? How can each and every element of this system, or each and every sphere of this system, how can we represent them in terms of mathematical notations? So over here we consider any two arbitrary spheres. Let us suppose S1 is equal to 0 and S2 is equal to 0 be any two arbitrary spheres from this collection or the system of spheres. We consider any two arbitrary spheres. Let us suppose that their equations are S1 is equal to 0 and S2 is equal to 0. Okay. Then then one can prove that lambda s1 plus mu s2 is equal to 0 will form a sphere. Lambda s1 plus mu s2 is equal to 0 will form the equation of a sphere provided lambda by mu is not equal to -1. If by chance lambda by mu becomes is equal to -1, then we actually obtain this kind of relation, and that relation will represent the equation of the radical plane. Our target is to construct the equation of spheres out of these two arbitrary spheres. Arbitrary spheres S1 and S2 will generate any other equation of the sphere provided lambda by mu is not equal to -1. And if we divide this relation number 1 by the quantity lambda, then we see that this equation can be written in this way. You see S1, okay, this S1 plus mu by lambda multiplied by S2 is equal to 0. So that would be the equation of a sphere. Now from this collection, of spheres, you see, for different value of mu by lambda, for different values of mu by lambda, we will get different equation of the sphere provided that mu by lambda or lambda by mu is not equal to -1. So we consider two different values. Suppose for the first case, this mu by lambda is equal to this lambda 1, and for the second case this mu by lambda is equal to lambda 2. So we consider two different values of mu by lambda. Over here we consider for the first time that mu by lambda is equal to lambda 1, then we will get the equation of a sphere. And over here if we put mu by lambda is equal to lambda 2, then we will get the equation of another sphere. Remember these two spheres over here, s1 plus lambda 1 s2 is equal to 0, and s1 plus lambda 2 s2 is equal to 0. These are actually two spheres generated out of these two spheres s1 and s2. And if we consider that these two equations represent two different spheres, then you see lambda 1 must be different for lambda 2, because if lambda 1 becomes is equal to lambda 2, then this equation will be identical with this second equation, and of course in that case both of these two would represent a single sphere. So in order to keep these two spheres different, the value of lambda 1 and lambda 2 must be different. Okay, and over here you see, if we consider the first expression s1 plus lambda s2 is equal to 0, then what would be the coefficient of x square? You see, s1 is this kind of expression, and lambda 1 s2, over here lambda 1 s2 means over here this coefficients of x square plus y square plus z square, it has to be multiplied by lambda 1. So how to compute the coefficient of x square or y square or z square? Then coefficient would be 1 plus lambda 1. That would be the coefficient of x square plus y square plus z square. So over here in this first equation, the coefficient of x square, y square and z square should be equal to 1 plus lambda 1. All right. Similarly, in this second sphere, the coefficient of x square plus y square plus z square, that would be is equal to 1 plus lambda 2. So these are the coefficient of x square plus y square plus z square. And if we call this coefficient is equal to a1, and this coefficient is equal to a2, then I have discussed earlier that the radical plane of these two spheres would be is equal to would be given by this kind of equation, that a2 s1 minus a1 s2 is equal to 0, as I discussed over here, that over here the coefficient was equal to a1, and in the second sphere the coefficient was equal to a2. So over here in place of a1 we are considering 1 plus lambda 1. We are considering 1 plus lambda 1, and in place of a2 we are considering 1 plus lambda 2. Okay, we are considering 1 plus lambda 2. Therefore the final expression in place of a1 we shall have 1 plus lambda 1, and in case of a2 we shall have 1 plus lambda 2. So the first relation would be multiplied by 1 plus lambda 2. The second relation would be multiplied by 1 plus lambda 1. All right. So over here, what is the first relation? This is the first relation. This is the first equation of the sphere. So this equation is multiplied by 1 plus lambda 2, and this second equation is multiplied by 1 plus lambda 1. All right, so in this way, if we now make all the manipulations and cancel them out, ultimately we will get this kind of relation. And as because lambda 1 is equal to is not equal to lambda 2, so we can cancel this lambda 1 minus lambda 2, this factor, and we will get that s1 minus s2 is equal to 0. And s1 minus s2 is equal to 0 is actually the radical plane of the first two spheres. So what we observe, that if we consider any two values of this parameter mu by lambda, on any two distinct values of these two parameters mu by lambda, then they would generate two different spheres, and the radical plane of these two spheres, is nothing but equal to the radical plane of the sphere S1 and S2. So in what we observe, that therefore we can say that in this coaxial system any sphere can be written in this way. And what is the property? The property is that any two member obtained from this system of spheres will have the radical plane as equal to S1 minus S2. So radical plane will always be same over here. Therefore, we can say that the coaxial system, the mathematical expression of coaxial system, can be written in this way: lambda s1 plus mu s2 is equal to 0, where lambda by mu is not equal to -1. So this is the mathematical expression of coaxial system of spheres. And along with this definition, let me introduce the definition of a limiting point. It may so happen that the radius of a sphere becomes is equal to 0. Hmm. And if the radius of a sphere belonging to this coaxial family becomes is equal to 0, then such spheres are nothing but the points. They would be point spheres. The radius would be is equal to 0. They would be point spheres, and such spheres are called limiting point of the of that family of spheres. Okay, so that is the definition of limiting point in the coaxial system of spheres. Now over here, let me discuss two examples. Um, Let us consider this kind of example over here. What does it say? It says that show that the spheres x square plus y square plus z square is equal to 64, and x square plus y square plus z square minus 12x plus 4y minus 6z plus 48 is equal to 0 touch each other internally. We shall have to show that they touch each other internally, and we will have to find their point of contact. So let us represent these two spheres by S1 is equal to 0 and S2 is equal to 0. What would be the radius of these two spheres? The radius of the first sphere would be is equal to 8, and the radius of the second sphere would be is equal to would be obtained by this relation, and ultimately we will find that radius of the second sphere would be is equal to 1. And what would be the centers of these two spheres? The center of the first sphere is equal to 0, 0, 0, and the center of the second sphere would be 6 minus 2 and 3. From these coefficients we can find out the center of the second sphere is 2. So let us call them by C1 and C2. Then what we can do, we can compute the distance between C1 and C2. Let us compute the distance between C1 and C2. That becomes is equal to 7 unit. And what we observe is that this 8 minus 1, that is equal to 7. That means R1 minus R2 is equal to the distance d, and this is the condition under which the given spheres touch each other internally. So this would be the position, this would be the external sphere, and this would be the internal sphere. So they are touching each other internally in at this point. Let us call it maybe the point P. Okay, let us call it the point P. Hmm. Now we'll have to find out the point at which these two spheres touch each other. Then what to do? We just solve the given equation of the spheres, and we can consider that kind of approach, or we can also find out the common normal to the spheres. You see, common normal can be obtained by this straight line. Just join the centers C1 and C2 and draw the straight lines joining C1 and C2. That would be the common normal. So we consider this is the center C1, and you see, if we know the coordinates of C1 and C2, we can compute the direction ratio of the straight line joining C1 and C2. How to compute the direction ratio? Just subtract these coordinates of C2 or subtract the coordinates of C1 from the coordinates of C2, you will get the direction ratios. So if we subtract them, ultimately we will get this kind of direction ratio, and the equation of the normal is passing through the point 0, 0, 0. That is the point center C1. So this would be the equation of the normal. And you see, on this point we consider any point on this normal. Say let us call this ratio is equal to r, and then any point p on this normal can be written in this way, that b is equal to the x would be is equal to 6 into r. Y would be is equal to minus 2 into r, and z would be is equal to 3 into r. So P may have this kind of coordinates. All right. And if this point P lies on both of these two spheres, you can consider any sphere, or any plane of contact. We can consider any plane. That plane of contact of these two spheres will look like this, the tangent plane. Hmm? So whatever the approach you consider, you can consider the plane of contact. The plane of contact can be found by subtracting the first equation number 1 from equation number 2. Then this would be the equation of the plane of contact. So if we just put the expression of P over here, if we put the expression of P in this plane of contact, then we will be able to compute the value of this parameter R. So we would get R is equal to 8 by 7. So if we put this value of R is equal to 8 by 7 over here, in this expression of the point P, then we will be able to find out the coordinate of the point P at which both of these two spheres are touching each other. So in this way, we can solve this problem. We can also consider another problem. Let us consider this problem that two spheres of radii R1 and R2 cut orthogonally. Prove that the radius of their common circle, that means common circle of intersection, is equal to R1 R2 divided by 1 plus divided by R1 square plus R2 square. How to compute this result? Let us consider this picture. Over here, this is one sphere and this is another sphere. Suppose this distance, this radius is equal to R1 and this radius is equal to R2, and you see, if these two spheres cut each other orthogonally, then this angle formed at this point P, this angle must be is equal to 90 degree. All right. And what would be the area of the triangle? You see, this distance C to C1, this much distance would be is equal to the base of the triangle, and this much distance would be is equal to the perpendicular of the triangle. So by the formula of the triangle, that half into base into perpendicular, we can compute the area of the triangle. So in this way, we can find out the area of the triangle PC1 and C2. We can find out the area of the triangle PC1 and C2. And you see, from Pythagoras theorem, we can say that this distance C1 C2, that would be is equal to R1 square plus R2 square. This quantity root over of R1 square plus R2 square. So in this way, we can find out the area of the triangle. And over here, we can find out the area of the triangle, and we can find out the distance C1 and C2. Now you see, this area of the triangle can also be found in a different fashion. Say this is the perpendicular distance, and then we can consider this distance as equal to the base of the triangle. So in that case, you see, the area would be is equal to half into base means the distance C1 C2, and let us consider this distance, that would be actually the radius of the circle of intersection. Let us consider that this radius is equal to d. Then the area would be represented by half into C1 C2 multiplied by d. And what is C1 C2? We have already computed the expression of C1 C2 is equal to square root of R1 square plus R2 square. So that would be is equal to half into d square root of R1 square plus R2 square. So over here we get two different expressions of the area of a triangle. This is one expression that is equal to half of R1 R2, and another expression would be this one, half of d into root over of R1 square plus R2 square. So if you compare these two expressions over here, in that case what we get? We get that d is equal to R1 R2 by root over of R1 square plus R2 square. So this is the final result that we were to compute. So these are the few examples regarding the intersection of the spheres. So that's all from this lecture.